Let me get your attention, please, so we can get started. Oh, I don't have any announcements apparently. But as you know, problem set 4 is due next Tuesday. There's a form set up for it. I want to reiterate something that I said at the beginning of the semester, which some of you may have paid attention to and others may not. I suggested that you adopt a strategy of looking at the problem sets as soon as they're posted. Not with the intention necessarily of sitting down and actually solving the problems, but of getting what the problem is into your head. I have a sneaky suspicion that, and I reinforce that suggestion by saying that it is a widely observed fact of human cognition that your brain will solve complicated problems while you're not paying attention. And I have a sneaky suspicion that this piece of advice and this observation about human cognition is in the unfortunate category of things that people, perhaps particularly young people, wave their hands at and poo-poo. But I want to actually reinforce it. I use it every single day. If I know that there's some complicated thing I've got to do later today, I will look at it in the morning so that my mind will start cogitating on it later, and I do so much better later in the day when I do that. If I have to walk across campus, get lunch, come back, and start writing my next lecture, I will sit down and spend 5 minutes reminding myself what the lecture is supposed to be about and what the hard part is that I haven't figured out, then go get lunch and come back. And I may not think about it while I'm at lunch, but I will then write the lecture more effectively. So I really strongly encourage you, in answer to the inevitable question that some of you have, which is how can I do better on the next midterm, this is one of the things that I actually suggest most strongly. Start taking advantage of A, the pedagogical value of the problem sets in the first place, and B, your hidden cognitive capacity for wrestling with the problems in the problem set by downloading them on Tuesday when they're posted, read through them, think about where am I going to get stuck, do I even understand how to begin this problem, and then put them away until Sunday night, see if I care. It will really help. Okay, are there any questions? Is there from your perspective, is there some obvious reason why this is doing this today? What? Same problem. This is not me. Oh, God. Annoying. Too bad. Okay, so we're going to finish up what we started looking at last time. What we not just started, but actually got quite a long way talking about, which is this quasi-hyperbolic discounting model, behavioral alternative to the exponential discounting model of Samuelson. And I'm going to back up a little bit and explain some of what I did rather too quickly at the end of the last lecture. And then we'll spend the rest of the time actually digging into this model because it's actually much more complicated than it looks, right? So it's this super simple thing where we just add one little parameter to an existing already pretty simple model. But the implications are pretty significant and complicated, and we're going to spend today looking at what those implications are and how to work with problem solving in this model. Sorry, I'm getting distracted by the buzz of chat in the background, so I just need to ask you to finish your conversations and give me your full attention. Okay, so here's where we were last time. A simple mathematization. So I said that we'd observe this key psychological regularity, which is that people have a taste for immediate gratification, or what we call present bias preferences. Yes, we discount next year. We discount 2 years from now more than we discount a year from now, and 10 years from now more than either of those. But we discount everything in the future way more than the present. Okay, we really like getting things now, or running away from them really hard now, which is good if you're trying to hunt wild beasts and you're either running after them or running away from them. You really need to have present bias preferences. So how do we incorporate this? Well, we take this discount function dt and we alter it so that for time 0, t equals 0, it's just delta to the t, which is 1. And for all other time periods, it's beta times delta to the t. And what that looks like is that we just take the, originally what we had was the utility of some plan is equal to the sum from t equals 0 to capital T, which is the end of time of delta to the t times u of xt. Now, delta to the 0 is 1. So pulling this piece out here, u of x0 with no beta or delta, that's exactly the same as the original model. But then all future periods just have delta to the 1, delta to the 2, delta to the 3, delta to the 4. And here, we're actually just going to stick a beta on top of all of those. And it's going to be the same beta period after period. It's not going to get smaller and smaller the way delta to the 1, to the 2, to the 3 is getting smaller and smaller. Beta is just going to stay in there, making everything in the future less important than the present. Okay? So let me just show you, let me just update a graph that I'll graph the discount function. This is time t, and we'll have periods 1, 2, 3, 4, etc. And here's d of t. Now, for the exponential discounting model, what we have is that for 1, right, here's 1, here's 0. And for period 1, it's delta. For period 2, it's delta squared. Period 3, it's delta cubed. Kind of gets hard to squeeze these things in. And you get something that slopes off like that, and it's going to asymptote to 0. Yes, right. So this here, that's d of t equals delta to the t. D of t, if I stick a beta in front of that thing for every period except the first period, so the first period is still going to start at 1. I mean, the period 0 is still going to be 1, right? Because I don't discount the present. And then, so I'm going to take my delta, which was this, and then additionally discount it by beta. Okay, so the first period is going to sort of steeply drop off, let's say, to here, and I'll call that beta times delta. And then in the second period, it'll just be beta times delta again, right? And then beta times delta cubed, like that. And so it'll drop off sharply, and then go into this sort of smooth glide path towards 0. And that sharp drop off, right, creates not a kink, but it's sort of well, it is actually technically a kink. But it makes it look more like a hyperbola instead of an exponential curve. And so we call this quasi-hyperbolic discounting. So there's this sudden jolt of discounting because of beta, and then everything else is just this much more gradual increase in discounting as you get further into the future because of delta raised to the power t. What does that do? Well, it does a lot of things. And let me just point out. So this is d of t equals beta times delta to the t, except for the first period 0. So one of the things that does is that if we're comparing t equals 0 to, say, t equals 1, the 1 period discount rate is beta delta. But if we're comparing t equals 1, let's say t equals 2, it's just delta. So the per period discount rate isn't constant. Between any other periods, like t equals 2 to t equals 3, the per period discount rate is also delta, and will continue to be delta on and on forever. But there's this change in what the per period discount factor is from period between 0 to 1 and 1 to 2 and on from there. Okay, so we have this sort of like sudden drop in discounting, which is sort of time inconsistent, and that's where we're going to get preference reversals, because when you're comparing the current period equals 0 to any future period, you've got beta, and when you're comparing any future period to any other future period, you don't have beta. You're going to change how you feel about things when the nearest thing in your plan suddenly becomes now. Alice. Why wouldn't it have additional jumps? Oh, in other words, why did I even put this line in at all? Oh gosh, that's a good point, and actually it kind of speaks to a question that's completely unanswered in this model, which is how long is that time period and what happens in there? And so, yeah, in some sense, doing this in discrete time. So one thing I would point out is that in discrete time, a discrete time function doesn't actually involve any lines, it just involves points. So when we can connect those lines together, it's a mathematical fiction anyway. It's just for convenience so you can see what kind of shape it has. So this connector here is irrelevant, really. It's just there so I can say quasi hyperbolic and move on. What actually happens, this might be a day, it might be a week, it might be a year, and we have no idea what happens in the very short term. Is it really a discrete jump? Is it just sudden? Does it just drop off quickly and then who knows? That's into the realm of neurology almost. But so yeah, so we don't know. Okay. Let me, so we're going to get into what happens when we look at actual economic decisions under this model in a minute. But let me first go back and complete the sort of like, right, I do this standard model, anomaly, behavioral model. And to complete that arc, I need to show you that this new behavioral model explains the anomalies that the standard model couldn't explain. So I showed you two, and the first one had to do with the fact that if you estimate delta in the exponential model using trade-offs between now and the future, the delta that you get depends upon how far in the future the trade-off you're posing lies, right? Is it 1 month, 12 months, or 120 months, for example? So this here is the table that I showed you from Thaler's 1981 paper, which is on DSpace. And he basically said, in exchange for $250 now, how much would I have to give you 1 month from now, 1 year from now, and 10 years from now? And I just want to remind you that these numbers were wrong in the handout last time, so I've corrected them. And what people said, the median answer was 300 for 1 month out, 400 for a year out, and 1,000 for 10 years out. And if you then back out the delta the way we did last time, you get different deltas, significantly different deltas. These may not seem like big differences in absolute terms, but when you put that into a model, if you put 0.83, if you discount something by almost a fifth, right, a month from now, and then you're going to exponentially magnify that discounting over 10 years, you're basically going to discount things 10 years out down to virtually 0. Okay? That 0.83 is actually an extremely small number for delta. For a 1 month delta, that's an insanely low number. 0.99 starts to make sense a little bit as a monthly. It's probably a little bit more realistic as a yearly delta, but these are monthly deltas. That's already a fairly small number. So here's the exercise I want to do. It's a little bit mushy, but it's actually quite interesting, and I think it gets at the point. Let me figure out what I could come up with if I applied the beta delta model to these numbers in a kind of quasi-plausible way. The fact that people are saying they're indifferent between, say, 300 in a month and 250 now under beta delta implies that for them, and this is all assuming that the instantaneous utility function is linear, is that they're saying that 250 is equal to beta times delta to the t times x of t, where in this case t is equal to 1. So I'm going to look at t equals 1. I already know that xt, the median xt, is equal to 300. What can I then infer about beta? Well, this allows me to say, that implies that beta is equal to 250 over delta to the t times xt. And what I don't have here is delta to the t, but let me go and say, all right, delta is a long-term discount factor, so let me take the longest term estimate I have of it and take that as a better estimate than the short-term estimates from the 1 month and the 1 year. So let me just take 0.99. This is where what I'm doing is a little mushy. Let's just take 0.99 as the best approximation we have here of the long-run discount factor delta. And let me plug that in, okay? Delta equal 0.99. And what I get is beta equals 250 divided by 0.99 times 300, which is approximately equal to 0.84, which is really close to what we estimated for delta, because in the very short run, beta is doing most of the work in this model. Because delta is a long-run thing, beta is a short-run thing, okay? Now, if I take this seriously, let's say this is my best estimate of delta, and this is my best estimate of beta. Now let me plug those back into the model. So that goes here, 0.84. Now let me plug that back into the beta delta model and see what this model would predict for people's for xt x12 and x120, these indifference amounts. If I had tried to predict what people would say they needed in a year or 10 years to make them give up 250 now. Okay, so going back to the same indifference condition, 250 equals beta delta to the t xt. If I know beta and delta, or if I have reasonable estimates of them, then I can say what xt has to be, and it's 250 divided by beta delta to the t. Okay, so my estimate then for x12, your 1 year indifference point, is 250 over 0.84 times 0.99 to the 12, which is approximately equal to $335. And my prediction of your x120, your 10-year indifference, right? Last time, when I took delta of 0.83 and said what does that imply for x120, I came up with 1.28 quadrillion, which seemed implausible. Under this model, you'll see why. It's 250 divided by 0.84 times 0.99 to the 120. Well, see, the thing is that 0.99 to the 12 isn't that different from 0.99 to the 120, because we've taken all of the short-term action, beta, and gotten it out of the exponent, right, the part that's exponentiated. And it just sits there constant over time doing its dirty work of present bias preference, and the long term gets to do its thing separately, the 0.99. And so this number is actually not that different from 335. It's approximately equal to $994. Okay? So I get 335 there, and 994. And not only are these numbers more plausible, they're actually pretty close to what I observed in the beta. Okay? And so I'm pleased with that. Even though it's not my model. I'm pleased with it. Does that make sense what we did there? Spend some time looking at this and think about why it works. Yeah, David. Well, so originally what I did was I took this number, 0.83, as an estimate of delta, because there was no beta in the model originally. I said, if that's my estimate, I'm going to change colors. If that's my best guess about delta, what does that imply about x120? In the delta-only model, the exponential discounting model, that would be 250 divided by 0.83 to the 120. And the thing is that multiplying 0.99 by itself a lot of times does not get small nearly as quickly as multiplying 0.83 by itself many, many times. So what we're doing here is we're saying, no, most of that 0.83, most of that shockingly low number was actually driven by beta, by a beta of 0.84, and then just a little bit of long-term discounting from one round of delta. So then when we progress into time, 120 periods, we're discounting, the discount factor is getting smaller, but it's not getting smaller by multiplying 0.83 over and over again. It's decreasing by multiplying 0.99 over and over again, which is just getting smaller a lot more slowly. Yeah. So that's the big thing, is that it allows us to get this big, massive short-term discounting. I mean, you look at the kinds of things people will give up in the future in order to get a little something nice now. It's crazy, right? I will raise this child for the next 20 years of my life just for a little action on the backseat of this car. I mean, that's big discounting. That is big, big discounting. So it's beta that's getting us that big time discounting without getting us like insane numbers for delta. But the other thing that's going on is that if I'm here now, and I'm not comparing now to the future, I'm comparing the near future to the distant future, we're actually capable of making pretty intelligent decisions about next year versus 10 years from now. We make ridiculous decisions about now versus 10 years from now. And so what's happening is that when I make choices between next year and 10 years from now, that's all just about delta. And it's this 0.99 or even higher number, right? And it just sort of slopes off gently. When next year suddenly becomes now, because I have moved through time by a year, all of a sudden that same trade-off, which is now this year versus 9 years from now, suddenly I'm now discounting that same future time period by a massively smaller factor because I've thrown in this beta. Okay? And that's what's going to wreak havoc in people's decisions. And you can see that having a model that doesn't capture that profound shift when the future suddenly becomes now would get us a lot of crazy wrong predictions. Okay, the other thing that I told you was about time-consistent preferences, and the example that I gave was the difference between asking you, would you wait 2 weeks for $5 a year from now? Would you be willing to wait 2 weeks for $5 now? Okay, and most people say they don't want to wait 2 weeks for $5 now, and what that tells me, and now I don't have to assume that the utility function is linear, it doesn't matter. But if you prefer $100 now to $105 in 2 weeks, and if I let the time period, be defined as 2-week periods, what that tells me under a beta delta model is that your utility from getting $100, not discounted because it's now, is, sorry, I'm going to back up a second. If you say that $100 now is strictly preferred to $105, well, let's just say weekly preferred in 2 weeks. Okay, that tells me under the beta delta model that u of 100 is greater than or equal to beta delta times u of 105, right? Because I've got both beta and delta included in your discounting between now and next period. And what that says is that beta times delta is less than or equal to u of 100 over u of 105. Let's not worry about what that means economically. It just gives us an upper bound on what your 1 period discount factor is between now and 2 weeks from now. That should just be a 1. Okay. So if you then tell me that $100 in 52 weeks is strictly not preferred, sorry, you know what? I do want to make all this strictly. I'm just going to make it all more clear. It's strictly not preferred to $105 in 54 weeks. What that tells me in the beta delta model is that beta times delta to the 26 times u of 100 is less than beta times delta to the 27 times u of 105. And I can just divide both sides of that by beta delta to the 26th, and what I get is that u of 100 is less than delta times u of 105. Yeah? And then I can rearrange that and say delta is greater than or equal to u of 100 over u of 105. Which is fine, because what that tells me, if I put these two things together, is that beta times delta is less than this ratio of utilities. And delta is greater. Well, that's fine, because beta is less than 1. So that's exactly what you would expect. So this preference reversal is explained by the fact that beta is affecting your short-term decision, but it isn't affecting the decision when both outcomes are in the future. It's only affecting decisions where one of the outcomes is now. Okay? Now, that doesn't mean it's going to affect all decisions, right? If I, instead of saying 105, had said some bigger number, I would eventually get to the point where this ratio is down here, and you don't get the preference reversals. And if instead of 105, I picked a smaller number, I'd get it to where that number was eventually above both beta delta and delta, and you wouldn't get preference reversals. That's why I said, even if you didn't exhibit a preference reversal when I asked you that question, I can change the numbers so you will. Because you've got a delta, and you've got a beta, and there's a space between delta and beta delta, and I can choose my numbers so that ratio of utilities is in between those two numbers, and I can get you to exhibit a preference reversal, unless your beta is equal to 1. I have a colleague named Shahar Kareev who is from Israel, and he said to me one time, I can tell you my beta is 1. I'm like, okay, I'm not going to mess with you. And I think that's just what growing up in a society that's always worried about being invaded by its neighbors does to you. You have extreme self-control, right? Beta equal 1. But I can tell you my beta is a lot less than 1. Okay. Okay, so here's the thing. This all looks very lovely, but the model is incomplete. It's actually incomplete in more ways than one. We're going to deal with the biggest way in which it's incomplete, but it's incomplete in other ways that some of you already pointed out, having to do with, well, how do we know how quickly beta goes away? Is it 1 week? Is it 1 month? Is it a year? Unanswered question. But the big way in which it's incomplete has to do with what people are capable of predicting about their future selves. So let's get into that. Okay. Consider a student with the following predicament. I'm sure none of you will be able to relate to this. There are 3 days: t equals 0, t equals 1, t equals 2. So one of those days is today, and we're trying to decide which day to do a problem set. Okay. It doesn't have to be a day. It could be different weekends. It doesn't matter. I think actually, so by the way, everything we're going to do for the rest of this period is in the second assigned paper for this section, O'Donoghue and Rabin doing it now or later. So each day, or I think in the paper it's each weekend, there's a different movie. And doing the problem set means missing the movie, and not doing the problem set means you go to the movie. Okay? And in the paper, I think that there's a string of 4, and I think they're defined as a fair movie, a good movie, a great movie, and a Johnny